Okay. Barring any more interruptions, we'll continue on, hopefully. Yeah, so this is an ionic compound, metal, non-metal. So when you put that into solution, it goes into ions, the same as your salt, the same as a whole bunch of things, any ionic compound. So just know that. That's what dissociation is. These don't dissociate. Now they separate. The molecule will separate from other molecules of this, but it doesn't break up into carbons and hydrogens. Hopefully everybody's got the idea of dissociation. Anytime you see, look, if you want to draw dissociation, it's going to look like that. It's going to look like positive and negatives. That's what it's going to look like. So if they draw that in a beaker full of something, then yeah, that's dissociation. Okay, name 3 colligative properties. All right. Boiling point elevation. Freezing point depression. Vapor pressure depression. Right? And we all know how those work. Boiling point elevation. The waters can't free themselves. They can't get free because of all the little things in there. Freezing point, they can't organize into those nice structured crystals because I've added salt. That's why your roads stay watery instead of freezing. And vapor pressure, if I have some things and then I have other things like salt or whatever I've added to the water can't get out as much because it's got things blocking it from getting out. That's all you need to know. Know these 3 things, please. Oh. And know that the more stuff I add, the higher this goes. So if I have a beaker and it's got a few dots in it, and then I have a beaker and it's got a bunch of dots in it, this one, the boiling point is going to be higher than this one. I think I saw that on the final. I don't know. Maybe I didn't. Maybe I'm imagining things. You know better than I do. You saw the final way back when, beginning of the semester. Okay. Molarity. We're skipping over 40 because that's dumb. Adding heat, yeah, it increased the rate of reaction. And then they didn't really show the other things that increase the rate of reaction, like increasing the surface area or adding a catalyst. They didn't show any of that. So that's what that chart should say, but whatever. 41, molarity. What is the molarity of a solution that contains 0.769 moles of NaCl and 2 liters of water? Well, that's easy. Molarity is moles over liters. So they just told me how many moles. 0.769 moles of NaCl. I'll try and use units as much as I can, but in how many liters? 2 liters of water equals, okay, 0.769 divided by 2. 0.769 divided by 2 equals 0.385. 0.385 molar. 0.385 molar solution of NaCl. Okay? Seems pretty easy. The next one, a bit more difficult. They give us the molarity, 0.139 molar. And they give us 23 grams of KCl. Well, we have to change that 23 grams of KCl into moles of KCl. Grams of KCl, moles of KCl. 1 mole KCl. Let's see, 39 and 35, that's 74.5. So, 74.23 divided by 74.5 equals 0.308 moles. And X liters of solution. So, remember, these two can switch places. 0.308 divided by 0.139 equals 2.21 liters. 2.21 liters. 2.21 liters. Is that right? 0.308, 0.139. Let's take a look. Just make sure we're doing the right thing here. 2.22 liters. Okay, so she's got the same answer as I do. Good enough. All right. Preparing a solution. How would you prepare a 0.5 liter 6? Okay, let's get rid of this. A 0.5 liter 6 molar solution of NaCl. NaCl, X moles of NaCl. Well, I can see here that 6 times 0.5 would be 3, so I'd need 3 moles of NaCl. Did it say KCl, sorry. Is that right? What am I looking at? No, NaCl. 3 moles of NaCl to solve for X. So what I would do is I would put in 3 moles of salt, and then I would add water up to the 0.5 liter mark. If you say you're going to add a half a liter of water, then once you put in your salt, it's going to rise and you're going to have more than 0.5 liter and your molarity is going to be off. So you're going to add to the 0.5 liter. Add up to. Remember that. Remember those key words. Add up to. Add up to. Add up to the 2 liter or add up to the half a liter or whatever you're trying to make. I don't just add a half liter of water. That's not how it works. Okay. What are the best conditions for making a soda that contains solid sugar and gaseous CO2? Well, first I would dissolve the sugar in there at a high temperature, especially if I was trying to get it over saturated, if I wanted a bunch of sugar in there. And then when I'm trying to get the gas in there, you want a high pressure and low temp. The reason why is if I increase pressure, it's going to increase the solvation. And if I, what did I do with mine? Where'd it go? Oh, there it is. Solubility of a gas goes down as temp goes up. So if I want a lot of gas in there, if I want a lot of bubbles in my coat, then I want to do it at a low temperature where it's high solubility, where I can get 90 grams of CO2 rather than like 5 grams of CO2. People keep missing that question. I don't know what to even say. And I'll even tell you what it says on the test. I think, because I think I remember, 2 atmospheres or 1 atmosphere. You want 2 atmospheres. And then the temperature was 10 degrees or 100 degrees. You want 10 degrees. High pressure, low temp. Okay. I believe that is just dead off the final, but I don't know for sure. You would know. You saw it. Did you see something like that? Hopefully you'll remember it. Hopefully you'll watch this video. I'm betting that no more than 30 of you are going to watch this video, which there's a secret at the end. Okay. In the table below, list properties of acids and bases. Okay, let's do this. Acids. Bases. We clean with bases. We eat acids. What else? pH less than 7. That is the less than symbol, people. pH greater than 7. That means 7.1 up to 14 is a base or alkali. Maybe we should do that too. Alkali. pH less than 7, 6.9 to 0 is an acid. Let's see. Tastes sour. Tastes bitter. Phenol. Phenol. To say pink. I'm not writing that word again, so just know that it's clear in an acid. What else? Oh, they react with metals. Acids react with metals. What else? Oh, they turn blue, litmus, red, turn red, litmus blue. I think that's it. Right? Right? Queen, E, yeah. Looks good. Looks like a good list. Pause the video. Go back. Pause it. Look at it. Live it. Strong acids and bases strongly light a light bulb and 100% or completely dissociate. Weak acids and bases weakly light a light bulb and do not completely dissociate. I think I said it enough in class. Strong acids completely disassociate or dissociate completely. Strong acids and bases completely dissociate. Okay. All right, on to page, where are we at, 11 minutes? Y'all are going to find this video so funny, I'm sure, because of all the interruptions. Maybe someone will walk in a minute. Okay, identify the following as an acid, base, or neutral. Soap, that is a base. Tomato juice, that is an acid. We eat it. Drain cleaner, we clean with it, that's a base. Distilled water is neutral. Bleach, we clean with it, it's a base. Litmus paper red, so if it turns blue litmus paper red, then it's an acid. pH greater than 7, that would be a base. Litmus paper blue, that would be a base. pH lower than 7, that would be an acid. HCl. HCl is like the universal acid that you're going to work with if you ever take another chemistry class. You're going to use this stuff all the time. You will know it's an acid eventually. Hydrochloric acid, the most famous of acids. Okay. Substance used to neutralize a weak acid is a weak base. Identify the conjugate acid and base pairs in the following. Okay, so we've got NH4 plus OH goes to NH3 plus H2O. Okay, so let's take these guys and go over to the other side and see which one donated a hydrogen. NH4 turned into NH3. Oh, I think we have our acid. He gave away a hydrogen donor. That is the definition, the Bronsted-Lowry definition of an acid. So that's our acid. That's our base. And remember, acids turn into conjugate bases. Bases turn into conjugate acids. Ta-da! Nothing hard about that. If you identify the acid, the thing that gave away the hydrogen, it went from 4 hydrogens to 3 hydrogens. I think I found him. A lot of people mess that up on the acids bases test. Okay, HSO4 plus H2O goes to H3O plus SO4. All right. HSO4 turned into SO4. I think he gave away the hydrogen, so he is my acid. Here's my base. I can confirm it. H2O on this side, H3O on this side. So he accepted a hydrogen. My base turns into a conjugate acid. My acid turns into a conjugate base. There shouldn't be anything easier in the world than that. Okay, where are we at? What is another name for a base? Alkaline, alkali, alkali, alkaline, whatever you want to call it. Alkali. Do not forget. Alkali. Base. Same thing. Base. How low can you go? No, y'all don't know what Public Enemy is. Expand your horizons. Get back to the old historical rap. Okay. What are the products of hydrosulfuric acid reacting with sodium hydroxide? So hydrosulfuric acid. So I have HS plus NaOH. Well, it's a neutralization reaction is what it is. It's an acid and a base. And if I mix an acid and a base, I'm going to get a salt and water. I'm going to get NaS plus H2O. Sodium sulfide and water. But you could have just said a salt and a water. That would have been okay too, I guess. And question number 59, what are the products of Hydra? Oh no. And question number 59, using the terms metal, non-metal, acid, and base, explain how you neutralized and formed product. Oh my god, now I gotta write it again. HS plus NaOH goes to NaS plus H2O. I'm not going to use metal and non-metal. I'm going to use cation and ion and anion. Okay, cations always come first. Plus, minus, plus, minus, plus, minus, plus, minus. So, what it looks like is the cation from my base, because this is my acid, this is my base, this is my salt, and this is my water. So the cation from my, the cation from my base joined with the anion from my acid and became a salt. And the cation from my acid and the anion from my base became water. Anion, cation, salt. Cation, anion, water. Hopefully everybody knows enough about that to do that. Okay, amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree. Well, that sounds like specific heat. And we know it because it's, just look at the units. It's joules per 1 gram per 1 degree Celsius. The amount of heat required to raise 1 gram of water by 1 degree Celsius. Okay. Or 1 gram of anything by 1 degree Celsius. Remember, there's specific heats for water and all the other things. Oh, all right. So, looks like we're going to use this Q equals C times N times delta T. Excellent. We're going to get into some specific heat calculations. All right, the temperature. This is the only time we can use degrees Celsius, isn't it? Yes, the answer is yes. Okay. So, oh wait. You know what? We are going to cut this off here.